Good morning, everybody. So let us go on with Dmitry Abanin lectures.
All right, good morning, everyone. So maybe let's start with any questions regarding what we discussed yesterday. Okay, so if there are no questions so far, so let's continue. And first thing we will consider today will be thermalization. And we can first go back and recall, how do we arrive at this notion of thermalization in classical systems, right? So in a classical system with n degrees of freedom, right? So for example, I could imagine having n particles, right? We have two n variables, right? We introduce momenta and coordinates pi, qi. Right, and then there is this notion that as your system evolves, right, as your system evolves, it actually explores, right, over time, all the possible configurations which are allowed by which are consistent with global conservation laws, right? So let's say, if I were to denote collectively momenta and coordinates, right, your system evolves according to its Hamiltonian, but then so we, assume, right, that the system would probe over time all the microstates with a given energy, particle number, and so on. Right, so there is this idea of dynamically exploring, right, explore microstates consistent with global conservation laws such as energy conservation. And this is what is known as the ergodic hypothesis, right? And this notion of ergodicity means that dynamically you can start from one configuration, but then go end up in more or less any other over time, right? And this gives rise to the idea of microcanonical distribution. Right, where essentially we look, right, at the ensemble of all the microstates with given energy, particle number, and so on. Right, so I could say that my probability distribution for all these coordinates is essentially, for example, if energy is my only conservation law, then it's just a delta function, right? Energy which corresponds to given set of P and Q minus my, total energy of the system. And notion of ergodicity, so it is a hypothesis, right? This is where you start when you build statistical mechanics, right? And from this idea of microcanonical distribution, then all the other things follow, including entropy, temperature, and so on, right? Now, if we really go back to microscopics and try to understand why, which systems are ergodic and which aren't, right? That's of course a has been a big field, right? Also in certain cases trying to prove, in certain simple cases trying to prove that systems are ergodic, right? That's a difficult task. So, but intuitively, closely related but not equivalent notion is that of chaotic motion, right? Chaos in classical dynamical systems. And here, right, the idea is that chaotic systems generally over some time scale, right, they forget their initial conditions. Right, and there is a notion of the Lyapunov exponent. So, for example, if I start out the system in state with some choice of p's and q's, right, and let me add vectors to emphasize that this is right. This is collective coordinates, and then I change the initial condition a little bit, right? That's so I just change p's and q's by a small amount. Right, then we expect that in a chaotic system, over time, these two trajectories would strongly diverge, right? And if I were to measure distance between x of time t, well, let me just write delta x of t some distance, so that would grow exponentially in time. Right, and this rate of this divergence, so that's the Lyapunov exponent. So, and generally, if you have a generic dynamical system with lots of particles, no special symmetries, right? You expect chaotic motion, and such systems are typically ergodic, right? Which allows you to use this notion of ergodicity, right? And then microcanonical distribution, Gibbs distribution, and so on. So most classical dynamical systems with sufficiently many degrees of freedom, right? Most classical dynamical systems are chaotic and ergodic. Now, of course, there is also, especially for few body system, right? So what we study in the course of theoretical mechanics is this notion of integrable systems. Right, so for example, if your system has some extra symmetries, right, in those cases, it can be that there are, there is one or more extra integrals of motion, and in the case when you have as many integrals of motion as you have, for example, particles in your system, right? So here, conservation means Poisson bracket with the Hamiltonian is 0. And okay, yeah, I will not write out Poisson bracket, but I guess that probably you'll remember. Right, so then we can make a canonical transformation and change coordinates going from P and Q to these coordinates action angle variables, right, I and theta. And then so we can predict dynamics because I's are integrals of motion, they would stay constant, right? So ij of t would be ij of 0 would be constant, and then so thetas would have some velocities, right? Because either they're conjugate variables, right? And then you would expect that theta of j of t just moves at a constant velocity, right? So you have some frequencies, omega, and then your initial condition. Right, so and clearly here, right, motion is very different. So you don't expect chaos, right? Motion would be regular, and then your trajectories would be tori. So if you're living on some compact manifold, then it would just keep going around around your space, right, making tori because these frequencies would be incommensurate. Right, so your trajectories would be tori in phase space. And simple, simple cartoon pictures of chaotic and integrable systems. So for example, if you, and of course, yeah, these systems have been studied a lot over the decades, right? If you consider a stadium billiard and you a bit larger. Right, and you have a particle there, then the system will be chaotic, right? So here you would get divergence of trajectories. But at the same time, if you consider some very symmetric billiard, like a circular, right, in this case, angular momentum is conserved, and therefore, in this case, you have integrability. Now, another important question is, of course, integrability is a fine-tuned property, right, generally. And you can ask how is it affected by weak perturbations. Right, so we can weakly perturb an integrable system. And ask whether, how and whether motion changes from this quasi-periodic motion to completely chaotic, right? Right, so what is the transition between integrability and chaos? And here, generally, I think there is a theory to answer this question partially, which is KAM theory, Kolmogorov-Arnold-Moser, and essentially what it does, it tells you that if these frequencies are not very commensurate, right, and then under certain conditions of sort of not being commensurate such that you cannot easily exchange energy between different degrees of freedom, right, some so most of the invariant tori would be deformed but survive, right? So it tells you there is certain degree of stability, right? But only for, strictly speaking, it applies for few body systems and weak perturbations. Systems, and there is this condition of frequencies being incommensurate, right? Right, so there is certain degree of stability, but it is believed that if you take a system of many particles and then even a weak breaking of integrability would make your motion chaotic. Right. So any questions or comments about this? Brief refresher about classical systems. Yeah. Mm-hmm. I understand. So I think you're bringing up an important point that indeed the fact of having many particles, that's important, right? Indeed. Right. Indeed. I did not emphasize it here, but indeed this is important for looking at a given state of the system and somehow saying that this is typical, this would be close to the Gibbs ensemble, right? Yeah. Right, exactly. So that relies well, I think ergodicity enters in the fact that, for example, if you do Boltzmann kinetic theory, right, there is an assumption of molecular chaos, right? That whatever initial correlations you had, they would get erased over time, right? And for me, that is related to ergodicity, right? That part of Boltzmann theory, right? That are typical, yeah, exactly. So it enters there, and then indeed. Yes, exactly, right. For me, they come together somehow, right? But indeed, that's an important point, because if I were to take indeed a system, for example, of few particles, right, which is ergodic, right, you're absolutely right that its instantaneous state would not have observables given by microcanonical ensemble. In this case, I would only get it if I average over time, right? So there is indeed this step also, right, that once you have sufficiently many particles, then more or less every configuration that you arrive at, right, after some initial time of scattering of particle would look like that with small deviations. Yeah, exactly. Thanks. That's an important point. Okay. Any other comments or questions? Okay. So, and with that, of course, this is extremely superficial, and that there are people who have spent their careers on these questions. So we are not doing it justice here, but really our goal is quantum systems, right? And this picture would be helpful to keep in mind, in particular to compare and contrast with what we would see in many-body localization, right? And also understanding how in interacting quantum systems, even the starting point for describing thermalization is a little bit different, right? And a simple, right, turning to quantum systems, right? For example, one immediate difference you see, right, is that instead of defining trajectory in a phase space, right, we have to deal with the unitary evolution of a wave function. So, for example, we cannot take this notion of chaos and blindly transfer it to, for example, defining chaos in the quantum spin system, right? Because, well, you would see that this immediately fails because, for example, if I take initial state psi 0, right, and then did you lose your pen? So, and consider another slightly different initial condition psi 0 prime, right? Then let's say their overlap initially is 1 minus epsilon. Then you know that during unitary evolution, this overlap would stay exactly the same, right? Because one gets multiplied by e to the iht, e to the minus iht. So it's a unitary transformation, and therefore they would always stay in terms of overlap exactly sort of the same distance from each other. Right, so we have to rethink a little bit how we view quantum chaos. And here there are several ways to define it and view it. And the first, so the first insight, and one definition and one way to probe quantum chaos comes actually from random matrix theory. Right, and there was a course already on random matrix theory, right? So I will just use a couple of facts and appeal to your intuition, and then we would see how it transfers to real quantum many-body systems. Right, so and here you could, I think one route that you can pursue is take a, for example, classical system and try to quantize it, right? And see how, quantizing chaotic system differs from quantizing an integrable system. But another route, and that's what emerged due to Wigner, right, in the context of complex nuclei, is idea of focusing on the statistical properties of eigenstates and spectra, right? Spectra of your properties of eigenspectra and eigenstates. So, and right, so at the time, at least part of the motivation was understanding patterns in the spectra of complex nuclei, right? And nuclei are right. You have many strongly interacting degrees of freedom. Right, so you can imagine a bunch of degrees of freedom, so and everybody interacts with everybody, right? And of course, the a natural way to model it in the first approximation is to say, well, let us consider a Hamiltonian which is completely random, right? So every state. So let me consider a Hamiltonian H, right, which is n by n matrix. So I have H11, yeah, like that. H1n, Hn, right? And if I think about this in terms of states of my system, right? So I have some basis, and then H II is the energy, right? So I have a bunch of levels with different energies, level 1, 2, 3, and so on, right? And then matrix element Hij gives me an amplitude for a transition between I and J, right? So, and here I consider Hamiltonians where there is no notion of locality, right? So I can hop everywhere between any two levels, right, with a pretty sizable matrix element. Right? So, and then you can say, well, let me make this completely random and Gaussian distributed, so probability of a given Hamiltonian would be proportional to an exponential minus beta over 2a squared trace h squared. Right, and here I'm, beta refers to the ensemble, to the symmetry of the Hamiltonian I consider, whether it's, real, orthogonal, or unitary. Right, so here I'm writing it for the orthogonal ensemble, but so I can write that this is, in terms of matrix elements, this is exponential minus beta 2a squared sum over ij hij squared. Yeah. Right, and the fact that this measure is actually invariant under unitary rotation makes everything easier. So you can get quite a few analytical results about the properties of these random matrices. Right, and one of the results which I assume you've covered, last week, is this idea of level repulsion. Right, and this arises because really, if you think intuitively about such a Hamiltonian, you expect your wave functions to essentially be spread more or less uniformly, uniformly over all the possible basis states, right, with random Gaussian coefficients. That's your expectation. And at the level of the spectrum, right, so what you would find is that it would be very unlikely to find two energy levels which are very close by, right? Because there would be, one of these matrix elements which is pushing them apart. And that, okay, so that you can see already if you study simplest case of a 2x2 random matrix. So you could say there is E1, and then there is off-diagonal matrix element V over square root 2, V over square root 2, epsilon 2, where all these three numbers are random variables. And then you would find that, E12 is plus epsilon 2 over 2 plus minus 1/2 square root squared plus 2 V squared. Right, so you see that to get, for example, if epsilon 1 and epsilon 2 are very close to each other, right, then for them to be, for energy difference to be less than some omega, right, that would require the off-diagonal matrix element here to be below omega. And if it's Gaussian distributed, right, probability of that is proportional to omega. So, right, P of omega is proportional to omega. And, right, so that leads to, of course, you can compute it more carefully, but that's the general idea. So generally, right, I'm just reminding you, I guess, what you've already explored in detail last week, right? So I'll just write an answer. So it tells me that the probability of finding two levels distance omega apart, right, would be proportional to omega to power beta e to the minus some constant that depends on beta omega squared. And beta is 1 or 1 and 2 for orthogonal, Gaussian orthogonal ensemble, and Gaussian unitary ensemble. Right, so if I were to plot statistics, right, distribution of level spacings now, what I would find is that it goes to 0 in some form here, right? Then it peaks and then it decays, because it's very, unlikely. You're very unlikely to find a big gap in the spectrum, right? Exponentially unlikely. And this holds, right? This holds not just for this 2x2 example, but for general random matrices, right? And you can have sort of nice analytical understanding of this level statistics, right? From thinking about joint probability distribution for the spectra. And this actually, so this is called Wigner-Dyson distribution, Wigner-Dyson level statistics. And turns out that it is a good, right? It is a good indication of your quantum system being chaotic, right? It's a signature, right, of quantum chaos. And right, so for example, if you were to consider now a quantum particle in a stadium billiard, right, you would find that actually its eigenstates satisfy Wigner-Dyson statistics. Now, what is, I guess at least at the first glance, is a bit more, right, a bit surprising is that this would be so universal, and this would also, as we would see, this also applies to quantum many-body systems, right? Even though they're not a priori, you start out with some local spin Hamiltonian, right? It doesn't really look like a random matrix, right? So, but this emerges for reasons that we will understand shortly. In terms of eigenstates, right? Eigenstates of random matrices. So I don't know, how much did you discuss? Yeah. Well, so for many-body systems, right, I would define chaos in terms of thermalization, right, and in terms of forgetting initial information about your state, right? So we will get to that, but you're absolutely right. So I think for few-body systems, often it makes sense actually to take this as a, sort of definition of quantum chaos. But actually, I wanted to ask you, so how much did you talk about eigenstates of random matrices last week? Good amount, right? Yeah, okay. So then what I will use, right, I would use essentially that, very naturally, so if I consider, so let me choose a basis, for example, could be the regional basis of my, where I started looking at this random matrix, right? And let's say psi1, psi-n are components, wave function components, right? Then we expect that essentially eigenvectors would be random vectors with Gaussian distributed amplitudes. Right, so I would expect that for eigenstate, so let me label eigenstates by n and m, right? So n would have amplitudes psi1n, psi-nn. So, and we expect that psi j m star, psi I n averaged, right, averaged over ensemble would be 1 over Hilbert space dimension. So here for me it's n, delta mn, delta ij. Right, so they behave, for a large, in the matrix they behave like essentially independent Gaussian variables. And then I can draw a couple of implications from this. Right, and one implication, so I could, of course, it's a little bit of a, this model is all to all. It doesn't have locality, so it's even a little bit difficult to think about a very meaningful observable. But nevertheless, I could introduce some observable O, which has some eigenbasis, right? And this is my observable. Then, first of all, we would find, so let's think about matrix elements of these observables. And this is something that we would use, right? We would use once we go to many-body systems. So it's diagonal matrix element, right? O MM. Well, let me first consider OMN, right, which is MON. N I psi I M star psi I N, right? And then if I, right, so these are random Gaussian variables. So if I average them now, right, I will get, right, so each one of these would give me, under averaging, delta mn 1 over n, and therefore I get 1 over n sum over OI. Right, so it's a average of eigenvalues of O, which makes sense because if I have a random vector, right, and look at observable over it, okay, it would just give me, right, a mean of eigenvalues. And then and then of course I have delta m here. Sorry, delta mm. So only diagonal matrix elements survive. And then naturally, if n is sufficiently large, then fluctuations would be small, would be suppressed as 1 over square root n, right? On top of that, so all the eigenstates would look kind of typical, right? They all would have this value of diagonal matrix element. And finally, I can also ask what is, so average value of diagonal matrix element is 0, but then I can ask what is, right, what is average value of a square, right? What is variance of off-diagonal matrix element. Right, so let me square it and then average. And then, so then we can, right, using a similar argument and just this, right, this expression for how, for the averages of wave function amplitude, so we can show that this is actually 1 over n O squared average. Right, where O squared average is a sum, right? Essentially, it would be defined in the same way. So O squared average is 1 over n sum OI squared. And that tells us, and so once again, we can expect that O and M's would be Gaussian distributed, right? And then we can write combining diagonal matrix element here and this result for the square of the off-diagonal matrix element. So we can write combine answer. So we can say, well, OMN generally would be O averaged, and here averaged over, right, over the full Hilbert space. So I mean, this is for me O average delta MM plus square root or squared bar over n. And then, since these are, I expect off-diagonal matrix elements to be Gaussian distributed, right? This would be RMN, where RMN is Gaussian random number with variance which is 1. Now, this part here, it has another interpretation, right? I could say, well, I'm trying to compute matrix element n m o n, and let me view it as a scalar product of vector m and then vector o acting on n. So both were random orthogonal vectors in the Hilbert space. I acted with some Hermitian operator on one of them. I got another random vector, right, which is no longer orthogonal to m, right? So this is actually scalar product of two random vectors, right? Well, up to some overall factor, right? So two random vectors, random 2 and random 1, and of course that, right, such a scalar product typically goes, its absolute value goes as 1 over square root of n, right? Because you can always choose your first coordinate to be pointing in the direction of R1, right? And then the second vector would just look like n random numbers which add up to 1. Right, so that's the intuition, right? So it all comes from this observation that your eigenvectors are random vectors in the Hilbert space. So any comments or questions? Because I guess you learned quite a bit about random matrices last week. So okay, so let's keep this in mind, right? And now go to our case of interest, which is, well, let me use this one, which is quantum many-body systems which have locality and have, a lot more structure than random matrices. Right, so, and we would see that actually quite some features that we are observing in random matrix theory, right, also apply some features also arise in many-body systems which have locality. Right? And that's, at the first glance, surprising, right? Because certainly, you know, if I'm, for example, considering Hamiltonian of the type we saw yesterday, so you have T plus interaction right? Everything here happens locally, right? A priori, I cannot hop very far away like in a random matrix, right? I cannot have density interaction with something far away. So how come you got Wigner-Dyson level statistics? And as we would see, actually, a non-trivial generalization of this result holds for thermalizing, for more or less any thermalizing many-body system. And here, so here let me just give you a little bit of intuition to build up to what we'll discuss in the second half. So let me start with such a system with local interaction. And let's say I do it sort of stage by stage. So I first diagonalize my chain, right? So my chain up to some scale L, for example, right? And then I join two systems with this coupling, hopping across the boundary and interaction, right? And see how the eigenstates get modified. So let's say I first, well, let me call it left and right system. And let me say that, for example, I have a bunch of eigenstates E alpha on the left part, and then a bunch of eigenstates E beta in the right system. And then, so what I'm going to do, I'm going to join them, right? I'm going to turn on this coupling, right? Let me call it H left right. And this would be a local coupling. So it would include hopping and density interaction, right? So this is left right interaction. And when I refer to this eigenstate, so that's for part of the Hamiltonian that acts only on the left or only on the right. And then so I can say, well, this interaction would, right, H left right, would have some matrix elements which can take me from alpha on the left, beta on the right, to alpha prime on the left, beta prime on the right, right? And physically, if my system is capable of exchanging energy between left and right part, I expect that this would introduce, so I can think now of alpha times beta, right, as some basis state. So I'll have, of course, lots of such states. And the interaction, right, so let me, sort of similar to how in a random matrix we had original levels, right, and we had hopping. So now let me think about first these product states as my basis states, and H left right as something introducing hopping, right? And intuitively, if your system can exchange energy, I would say, well, let me prepare left system in eigenstate alpha, right one in the state beta, right? Then for system to come to equilibrium, this level has to be coupled to sufficiently many levels such that there is sort of a golden rule decay, right? And you fall to, right? You equilibrate, and the energy comes to, there is energy redistribution towards some equilibrium state where there isn't large imbalance in terms of energy between left and right part. Right. So and then you would say, well, if this happens, then my combined eigenstates n are more or less Gaussian random vectors, and in this basis, right, in this basis of product eigenstates, if you wish. Right, and then if you wanted, I'm not suggesting one can turn this to really rigorous argument, right? But at least it can give you an intuition for how and in what sense eigenstates of this many-body system start looking more and more like, in some ways, those of a random matrix. And what we're going to do next after the break, so we will use this intuition to formulate an ansatz for matrix elements, right? And then you can go back and see that this is actually all consistent, that if we were to then do this trick with combining two systems and look at matrix elements, it would look like, in some ways like a random matrix, right? And in fact, so why this happens, because actually states become very entangled, right? And turns out that entangled states like that, they're very good at mixing, and they have large matrix elements, which tend to hybridize them. So okay, so any questions, Andrea?
Regarding this last example, you say that A alpha beta is more or less random, but it shouldn't not depend for typical local interaction on the different apparent E alpha minus E beta.
Yes, absolutely. So it would be a random model of this constraint. So here I have to ensure, right, that E alpha minus E beta is less or equal than the norm of this connection, right?
But within that is somehow random.
Yes, right. In the first approximation, yes.
And this cutoff could be also smaller depending on how the system is.
Yeah, exactly. Right. That's an important point. So we would see that, of course, naive random matrix theory is not enough. We'll have to supplement it exactly with some more information about, right, about our systems coming from this fact that energy is a sum of local terms, right, and also put some extra information about dynamics that we have in the system. Right. If there are no other questions, so shall we go for a break and come back in 10 minutes? Thermalization in many-body systems in state and really what is very powerful is the set of ideas that is called eigenstate thermalization hypothesis. ETH. And this was, I think, in some some aspects of it really come from random matrix theory and go back to, in particular, Wigner, but the more recent ideas are due to Deutsch and Srednitsky. Right, so let us consider generic many-body system, for example, a spin system with local interactions. And what ETH tells us, right, that if the system is thermalizing, in the sense that from, starting from a physical initial condition, it will evolve to a state with effectively thermal observables, right? Observables which would be consistent with microcanonical ensemble or Gibbs ensemble at the corresponding energy or temperature, then you can make an ansatz, right? Ansatz for matrix elements in the basis of eigenstates of H, in eigenbasis of H. Right. So in other words, and sort of it goes both ways, right? So you expect that with this ansatz, right, you would get thermalization from a generic initial physical condition, right? And this ansatz, so let me look at the matrix element of a physical observable O one by one and define the new things that appear. So E bar is average of the two energies En and Em. Omega is their difference. And then S of E bar is thermodynamic entropy at energy E bar. Right, and further, right, there is further assumption here that O of E bar is a smooth function. And here, yeah, we should distinguish O of E bar, which is a function, from O, the operator, right? So I'll, put mostly heads on operators, and this would be just a function. It's a smooth function, and moreover, this is identical. So O of E bar is identical to value of this observable over microcanonical ensemble at the respective energy. Right, so what we see from this is that a single eigenstate would already have observables like a microcanonical ensemble. And right, further, so R and M is random. This number here is random with variance 1. And FO is also, right, so this function we will talk a little bit more about in a second, but this is also a smooth function of both E bar and omega. And you see that this looks quite like the random matrix result we had, right? So in particular, this part, right, is very much like random matrix result. So you just, your diagonal matrix element is given by some average, right, average value of this observable over eigenstate, with only difference that here you have to look at a particular energy, right, and not averaging over the whole space. And in a second, we will see that this function, right, gives us actually dynamics of the observable. And finally, this factor, right, is just effectively tells us the effective Hilbert space dimension we have to be dealing with at a given energy, right? So that factor used to be 1 over square root n for the random matrix case. And let us see that ETH ansatz implies thermalization. Right, so well, first of all, we can use, right, we can show first that in the long time limit, value of observable would become essentially macrocanonical. So let me average now over time. So taking a limit t0 going to infinity, 1 over t0 integral 0 to t0 dt of t. And then so I can go back to our expression for expectation values of observables. Remember there was a piece coming from diagonal matrix elements and the off diagonal, right? And the off diagonal piece had the factor of e to the I en minus emt. So if my energies are not degenerate, then when I average it in the long time limit, I'll get a 0, right? For n not equal to m. And then I'll be just left with, right, just left with the diagonal piece, which is cm squared, right? Amplitudes, cm's are amplitudes of my initial state over eigenstates, or mm, right? So I remind you that psi of 0 is sum of cm m, where m's are eigenstates, right? And we see that this is essentially average over expectation values of or mm with the corresponding weights of your initial states. Now, yeah.
But if we have degeneracy, so that is assuming that the energies are not convergent.
Yes, right. So this is so if you have degeneracies, then you'll have to you will have to worry about those matrix elements, yeah. But these are so in light of, for example, Wigner-Dyson statistics, right? This would be really very improbable in a thermalizing system. And then you can see that, you know, ultimately physically you expect this function to really depend on the energy density, right? And in the typical physical initial state, energy fluctuations are subextensive, right? So typically you would expect that energy fluctuations are subextensive, so they go as square root of the system size L, right? So, and therefore fluctuations of energy density, right, delta E by L goes as 1 over square root L. And therefore you expect that this would be dominated, right? This would be dominated by the average density of your initial state, average energy density of your initial state. And right, this would give you that actually this is approximately, well, let me maybe make it a little bit more careful. So then I can say that, well, this is right, sum over m cm squared, and then OMM is O of E bar, right? So this is O of E bar, sorry, O of E, right? Plus EM minus E dO by dE at E average plus 1/2 EM squared d to O right? So I just Taylor expanded, and then I would see that, so E with brackets, that's the expectation value of energy of my initial state. So I would see that this term actually vanishes, right? And this term would give me something proportional to the fluctuation squared of my fluctuation of energy squared of my state, right? But this derivative would give me, right, inverse factor of the system size also, because because I expect that O of E is actually a function, right, of energy density, right? And this gives you, right, a reason to see that this term becomes negligible as your system increases, right? And actually, this becomes approximately equal to the microcanonical value at the corresponding energy. Right, so this is our first result, right, that under ETH ansatz, we expect the system to thermalize at sufficiently long times. So, yeah. Right. Yes, yes. Yes, that's an excellent point. So you're absolutely right that this argument is, tells us that at extremely long times, right, at infinite times, it will thermalize, but it doesn't. Of course, it's not very convincing yet for the reason you're mentioning, right? That in a many-body system, the smallest level spacing is very small, right? So a priori, if you really took this at face value and said, okay, I have to wait until time that's longer than this Heisenberg time, which is inverse level spacing, right? This would be forever. So in fact, you can expect something much faster, right? And this is because essentially to get there, you see, to understand this approach to thermal value, we need to understand off-diagonal matrix elements, right? So here, this would enter, right? This would enter, and then the fact that I have many eigenstates with this randomness here, this would just give rise to some smooth, right, approach, which would be determined by this function, right? So thermalization timescale, ultimately, that's an interesting question, right? What really determines the relaxation of the slowest modes in your system? And typically, in a sort of not very special thermalizing system, you would expect that there is, for example, slowest modes are related to, for example, diffusion, right? Diffusion of energy density, right? So, and those go, right? Those would go as a power law, right? Times go as some inverse power law of your system size, right? So that's your expectation. But indeed, yeah, an excellent point. So, any other questions or comments? No. Okay. So so then we can also, right? So we can also show that not only this average would stay close to a thermal value, but also fluctuations around thermal value would be negligible. Right, so in particular, temporal fluctuations are negligible. And to get that, so let me consider a similar long time average. dt O of t squared minus, right, minus long time average squared. And then I can go through the same exercise of, plugging, right, plugging my initial state in terms of eigenstates, matrix elements, and then after a little bit of algebra, I'll get sum over mn O mn squared cm squared cn squared. And so here m over not equal to n. So I'm not deriving it, but this is relatively straightforward. And then I can see that this would be less or equal, right, than maximum over OMN squared, and that we expect to go as e to the minus s e bar, right? So, and if I'm talking about, for example, about infinite temperature states, then effectively this is the inverse Hilbert space dimension. So this goes as 1 over 2 to the power L, right? So it is really goes to 0 quickly as you increase the number of spins. Right, and therefore we see that temporal fluctuations are actually negligible, so your observable starts out of equilibrium, settles to macroeconomical value, and then stays there with very little fluctuation. Now, maybe an important comment to make, which we haven't yet made, so you can ask which operators satisfy ETH. And here the answer is it is operators which are physical, local observables, such as for example, I can consider an observable which is sigma z operator on some site, right, or product sigma z operators on two different sites somewhere in the system, or a sum of local terms like that, right? So but it always has to be a relatively simple operator, right? So for example, sum of local terms, because clearly, right, there are very complicated operators which do not satisfy ETH, such as projector, right, projector onto a given eigenstate, onto an eigenstate. So Pn, well, let me call it PL, which is LL, because this would have expectation value 1 for eigenstate L, and then 0 for every other eigenstate. Jerome? They can be far away, yeah. Yeah, right. I guess you mean rather than local. Yes, yeah. Right. You're. Yeah, right. Because as I said yesterday, locality I will define a little bit differently depending on context. So indeed, these are few by the observables and their sums. Yeah, exactly. Thanks. So let me indeed say here few body. Okay, any questions? Well, they would actually. So yeah, they would. They would. So it's really I mean, it's not. I think it's not often that people study, right? People study ETH, for example, for those operators, right? But still, those are relatively simple observables you can measure, right? Right, right. Yeah, they're extensive, but their structure is relatively simple, right? So it does not a priori, it does not require exponential number of measurements, right? So okay, that's a good point. So let me maybe think about it, and then right we can maybe refine this a little bit further. Okay, so then there is one more, and okay, maybe let me just add just to give you also an example of a model that is thermalizing. No, they don't. They don't, because so if I were to plot expectation value, right, PL MM as a function of eigenstate number, right, there would be, so when M is equal to L, it will be 1, right, and then it's 0 otherwise. So it's like a delta function, so it's not a smooth function of energy, right? And as a simple example of a many-body thermalizing system, for example, I can consider transverse field Ising model, so sigma IZ, sigma I plus 1Z plus HX sum sigma IX. So this model would be integrable, right? Because I can map it onto free fermions by Jordan-Wigner transformation. But then if I break integrability, for example, by adding longitudinal field along z direction, right? So this term in the fermionic language would carry Jordan-Wigner string, so it's no longer integrable, right? So this is integrability breaking perturbation, and this simple chain, right? Simple chain would satisfy eigenstate thermalization, and yeah, generally it would be thermalizing for some generic choice of J, HX, and HC. So it's a very nice, right? It's a very nice sort of laboratory where numerically you can probe ETH, and this is a very robust. Of course, thermalization is a very robust thing. So even on a chain of 15 spins, you already would see very nice, right? Very nice eigenstate thermalization. And now, so let us discuss the response function relation between ETH and response functions. Right, so I can now ask, for example, if I were to study correlation function, right, of autocorrelator of t of 0, right, over, and let me evaluate it over an eigenstate, right? So I can insert resolution of identity in between, and then I'll get sum over n mn of t m, right, m o n, and then this phase is, right, this time dependence would just give me a phase, so then it becomes sum n o m squared e to the I e n minus e m t, right? And then I can go back to, right, I can go back to the ETH ansatz and see that time dependence would come from the piece where m is not equal to n, right? So there would be a diagonal piece, but I don't care about it. So there would be n o n squared plus, it would be sum over n not equal to m e to the I e n minus e m t fo e bar omega squared r and m squared e to the minus s of e bar. And this really, right, so I have this factor, right, I have this factor which comes from the Hilbert space dimension, but then I'm also summing over a lot of states, right? So effectively this will disappear once I go to the integral and integral over energies, because there would be density of states there which would cancel that factor, and then r and m I can just average and forget about it. It would give me 1. So, and this becomes, right, integral e to the I omega t fo of omega squared. So let me also forget about this e bar because it's just a parameter, d omega, and then I have still diagonal part, but so let me just keep it for completeness. Right, so, and this tells us that actually, right, this correlator is determined by the Fourier transform, right, Fourier transform of f omega, so that's effectively f o is gives me the spectral function of the observable. And here, right, you see that, of course, ETH ansatz is very general, right, and it's very nice, but it doesn't, you know, it doesn't do any miracle, so you still have to have an input sort of from the physics of your system to understand this function f, which determines response function, right? So, and depending on the observables and the system, this can have different behavior. So, and there are some, right, general expectations. So fo determines time-dependent response of observable O, and clearly it is both system and observable specific. And one interesting example is when this observable represents density, local density of a conserved quantity. So for example, you have particle density or energy density. So let me assume my system has particle number conservation, right, U1 symmetry, and then I can consider O, which is density, particle density on site I, right? density on I. So for example, if I go back to our example with spinless fermions, right, that's an example of a model where particle number is conserved. And then, so oftentimes you would, for the dynamics of density, you would see diffusion, right? For dynamics of conserved quantities, your natural expectation is diffusion. Therefore, you expect that, right, on physical grounds, that if you have diffusion, then n of t of 0 goes as 1 over square root of t in one dimension. Right, of course, in other dimensions, you would, this would go to the power, right, to the power which corresponds to the dimension of your space. And therefore, so that gives you FO of omega squared, which is Fourier transform of this, and which is 1 over omega, 1 over square root omega. And then if you have a finite system, right, there is a smallest energy scale, so longest time scale, which is when diffusion saturates, so that's your slowest diffusive mode. Right, so you have slowest diffusive mode, which corresponds to wavelength 1 over system size, right, and diffusion time which is of order L squared over diffusion coefficient. So D is diffusion coefficient. And this is called the Tauless time. And then I can define the corresponding Tauless energy. Right, well, H bar D over L squared. And then I expect that, effectively after that, there would be no more dynamics, right? So at energies below Tauless energy, this function FO saturates and becomes constant. So I can sketch this, right? I can sketch this now, this behavior of function FO or spectral function, if you wish. Right, so let's say FO of omega squared, omega. So I have first this 1 over square root omega. Then at the Tauless energy, there is saturation, right? And then there is only one more piece of the puzzle. So what happens, especially if I'm thinking about a lattice model, right? So what happens once I go to energies which are of order 1, right? Which are of order of hopping or interaction scale, right? So let me call this scale, for example, J, right? This is your lattice sort of interaction, local interaction scale. And then turns out that locality also imposes some pretty strong constraints on how the matrix elements behave at large energy separations, and then you can show that this actually, right, this actually starts decaying exponentially beyond that energy. Right, so, and that corresponds just to the fact that your system cannot do very much on at very high frequencies. And this part, actually, we will come back to it because this part turns out to be closely related to pre-thermalization in lattice systems. And yeah, so that's right. You see that there is quite a bit of structure, and then going back to random matrix theory, you could say, well, within Tauless energy, right, these states really look like random matrix eigenstates, right? But there is life beyond, as you go to larger separations, right, having to do with the fact that your system is ultimately local, there is dynamics, right, and your energy is the sum of local terms. Okay, any questions? Yeah. Is there? Yeah, okay. Right. So okay. So let's conclude with a couple of remarks about what we discussed. Right. So first of all, thermalization and entanglement. Right. So we expect that effectively eigenstates in thermalizing systems have thermal observables. Right. They look like microclinical ensembles or Gibbs ensembles. Right. So they're already like thermal ensembles. And therefore, if I now look at a state of a subsystem A, right, rho A evaluated in a pure eigenstate would actually look thermal. Right. Therefore, if I compute entanglement entropy, it's just von Neumann entropy of a thermal state, so it will be, like thermodynamic entropy. Right. So in this case, entanglement entropy is equal to thermodynamic entropy, entanglement entropy in an eigenstate. And that, of course, scales proportional to the volume, right, volume of my system A. So I expect generally a volume law entanglement. And also, if I think about the dynamical experiment, yeah. Yes. Yeah. So I'm taking an eigenstate, right? Yeah. Right. And this is also what I would observe dynamically if I initialize my system in some, physical state. I let it evolve, and it starts looking like a thermal state, right? And then once again, I will, for example, if I started from a state which is, a product state, then pretty quickly I would see, and I would look at dynamics of entanglement, right? So maybe I started from an unentangled state, so entanglement was 0, but then I am reaching thermal state, and then entanglement grows and reaches volume law. Right. So thermalization is accompanied by growth of entanglement to thermodynamic values, and that makes, in general, this makes describing process of thermalization in a many-body system rather challenging, right? Now, of course, you can argue, well, actually, you arrive at the state which does not have so many features, right? It's a thermal state, right? But otherwise, all these details of what its exact wave function are not very relevant for physical observables. And indeed, you can try to come up with, clever strategies of how to discard this information that is not useful. Right? So the real task, going back to this question of finding useful quantum advantage, right? That's the challenge, to find states which are very entangled, yet they have some non-trivial structure which has to do with entanglement, right? And that's not so easy exactly because entangled states tend to sort of mix and thermalize, right, losing any individual sort of features. So that's why it's a very non-trivial, very non-trivial task. But that said, of course, if you have an interacting system in let's say, in 2 dimensions, right, and your thermalization timescales are not incredibly short, then a priori describing thermalization dynamics, it does get difficult. Very good question. No, it's relevant, right? So there would be, right, a little bit of life here, and that would be this remaining life would be the tauless time, right? But indeed, this is not the best way to, see the tauless time. Right. So, for example, because fairly quickly, right, you get a lot of entanglement, and it's just the slow modes keep moving. Yeah. Also very good point. And sort of a related issue is scrambling, right? Scrambling of quantum information, which has to do with the fact that, if your system thermalizes, it forgets where it started from. And this manifests itself. So, for example, I could say, well, let me start out my spin system in some state, right, where a given spin I had observable sigma I z, which is +1. And as my system evolves, so it's unitary evolution, so this information stays in the system, right? But it gets now shared between too many degrees of freedom, right? So I think about u of t e to the minus iht, right? And sigma iz of t u of t, right? And I can think, well, this operator, right, expectation value is still 1, but at the same time, in a thermalizing system, this would become really a very complicated operator, so I could expand it in terms of elementary observables, which are products of Pauli matrices on different sites, right? So then it becomes sum of A alpha 1 alpha L, right? And then I have sigma 1 alpha 1, sigma L alpha L, right? So that's the general expansion of an operator over basis of products of Pauli matrices. And it started out as a simple operator, right? Just one amplitude here. But as the time progresses, right, these amplitudes would start becoming non-zero, right? And we have this phenomenon of operator spreading, right? Such that it really becomes this complicated superposition, which is not really measurable and would not have bearing on physical observables, right? So there is an interesting, also an interesting connection to operator spreading and how operator spreads in quantum many-body system. That also gives you actually a nice way to probe quantum chaos. Right? That's another route to tell that your system is chaotic. How do operators spread? And so, for example, maybe you've heard about things like out of time ordered correlation functions. Later's OTOC, right? So this is related to operator spreading, and yeah, we would not have time to really go that direction, right? But at least to give you some intuition, so that's very closely connected with process of thermalization in the Hamiltonian systems. Of course, you can also you can study other models of operator spreading if you have random unitary circuits, right? Which, of course, random unitary circuit that facilitates some some analytical calculations in the same way as random matrix theory does. So, and bless you. And right, and maybe let me just make a final comment before we break. So I guess now we have a longer break, right? 20 minutes. Yeah, okay. Yeah, I think maybe we'll do 20 and then just use. And maybe let me just make a final comment about thermalizing systems. Right, so we had, in the classical chaotic systems, we have this notion of Lyapunov exponent, right, and so on. For quantum chaotic systems, there is another type of sensitivity, sensitivity of eigenstates to perturbation of your Hamiltonian. Because I can say, well, let's say I have a Hamiltonian H and it satisfies ETH, right? So H, M, E, M, M, and let me say that ETH holds. Then I could ask how stable or unstable are these eigenstates under perturbation. So let me say add some, some perturbation. Could be a local, changing a local field slightly somewhere, right? So that's some simple, perturbation. And let me ask, so does it significantly, at which epsilon does it significantly modify the eigenstates? And for that, okay, so we actually have an answer thanks to ETH. So what I need to do is to go to the basis of eigenstates of, right, eigenstates of H, right? These are my eigenstates M. And then as usual, so perturbation would introduce hopping, right, hopping between these eigenstates. And the matrix element is given by epsilon V and M. And if it's a physically reasonable operator, I have ETH, right, then this would go as epsilon over square root of the Hilbert space dimension. So let me just, look at infinite temperature. So this is epsilon over square root of 2 to the power L. But the thing is that this matrix element, it's actually much greater than the typical energy separation between, right, typical energy separation between nearby levels, because the level spacing typically is, 1 over 2 to the power L. I mean, in practice, it's not 1, but square root L, but let me not worry about the subleading factors here. Right, so this tells you, and and once the matrix element is much greater than energy separation, then the states would get hybridized, right? So you can no longer do perturbation theory, right? You have to do degenerate perturbation theory, and you expect that that your states would be superposition of states which are within some energy shell. So you see that already for epsilon star, which is as small as 1 over square root of 2 to the power L, your eigenstates would be significantly perturbed, right, and start changing. Right, so and in this sense, what distinguishes these quantum chaotic systems that even very weak perturbations change eigenstates significantly. Right, and here you can see that in a certain energy shell, right, ETH ansatz here would imply that essentially it looks like a random matrix in some, right, in some within Thouless energy. So that's how it emerges, and then you can also use a similar logic to go back to our intuitive argument. How does, why does ETH emerge in many-body systems, and consider this trick with gluing to systems that satisfy ETH, and then see that their union would also satisfy ETH, right, generally. Because once you join them, there are lots of resonances and it starts looking like a random matrix. So, and I think this is a good place to stop. So any questions? Mm-hmm. Ah, yeah. Uh-huh. Another excellent question. Well, as you know, as I mentioned, ETH ansatz really it is quite basic in the sense that all the physics is hidden in this, right, in these functions. And indeed, you know, that's an interesting question. What would we need? Would we need extra information to compute higher order correlators, right? Or correlators of different operators, right? And the answer is yes, we would need to put extra stuff. And the simple, you know, a simple nice example, I think, is to say, well, let me consider, right? Let me consider two operators. Right, A acting on a spin here, for example, right, and then B acting on a spin far away. Then in systems with local interactions, there is also, right, this very nice result, which, you know, might seem obvious, but it's actually very useful, which is Lieb-Robinson bounds, which tells you that there is a finite velocity for spreading correlations. And therefore, if I were to go and compute the correlator using ETH, right, I would have to get something that satisfies Lieb-Robinson bounds, right? And that's so that we have to input extra in the correlations of matrix elements of A and B between eigenstates, right? So you're absolutely right, and that's actually somewhat surprisingly, I think this is the direction that only people started looking at more in recent years, right? Although, I mean, I think from this argument you can see that this must be, you know, Srednitsky ansatz must not be sufficient for everything, and it's not. Right, because you have extra, right? You have locality, and then you have physical constraints which come with that. Yeah. Okay. Any other questions? I guess everybody is ready for a coffee. So let's come back at 11:20 maybe, if that's okay. Yeah.